I'm really grateful to be here today. Let me say at the outset that I am not a GNU radio expert, but I have been a GNU radio user for many years. My research group at Notre Dame was basically built around using GNU radio and Edis hardware in the earliest days. So when Derek invited me to give this keynote, I thought I would reflect a little bit on what we've done over the years. So it was kind of a walk down memory lane. And then I tried to come up with some suggestions for this community to consider. Then I want to end with a little bit of an overview of a new center that is launched about a year ago that we're leading, and encourage you to get involved in that center. So to give you a little bit more context, here's a quick summary of my background. I did undergraduate degrees at Washington University in St. Louis, and there's two important points I want to make about that. Number one, there was no such thing as computer engineering in those days at this university, but we could get an EE degree and a CS degree in 4 years if we took just the right courses. So I got just enough CS in my system that the notion of software-defined radio was something that was interesting to me as I kind of continued my studies. The other point I want to make is that the gentleman sitting over here, Matt Edis, was an undergraduate as well at WashU at the time. We took digital communication systems together. And so it's great to see him, but it was also a fun ride. That class inspired me to pursue advanced degrees. I had the fortune of going to MIT. And at MIT, I got to meet someone by the name of Vanu Bose. May he rest in peace. But I was really inspired by his approach, and his PhD thesis, of course, was all about software-defined radio. I ended up doing a lot of theoretical work in my thesis, but then when I got a job as a faculty member at Notre Dame, one of the first things I did was start to build up laboratory capabilities using software-defined radios, and in particular, we got an early version of the original Edis USRP version 1, maybe even version 0 at the time. It was a beta, so I still have it, by the way. I don't know if it's going to sell at auction like the Apple ones, but I'm going to hold on to it for a while. So that trajectory has really set me up, again, with this perspective of communication system design, but with a lot of software awareness and using software-defined radio tools for pursuing research and teaching. I don't think I need to tell everyone in this audience that there's a lot of really exciting things going on in wireless or even radio systems more generally. And in particular, There's an incredible amount of pressure on the radio spectrum here in the US and around the world, given all this advanced technology in many applications. And so thinking about management of the spectrum, even software-defined spectrum management, is a pretty compelling storyline. So the way that we've approached research over the years has been to really try to blend theory and practice to make sure that the theoretical models, the algorithms that we developed are based on some sense of reality. We don't assume away too many important details. And so we've always tried to prototype in our labs. And software-defined radios have always been the right tool for my group. So thank you, Matt, and thank you, GNU Radio community. The goal has been to have a feedback loop here. So a couple of times around, we've gone to try to implement something, and we realized something was wrong with our model. We missed something salient, and so that gives us the opportunity to update the model and improve the algorithms, make them more robust, and so on. Along the way, we've had the fortune of having a lot of industry and government agency collaborators, which we're grateful for, and also a significant amount of funding to do this work. The other thing I want to let you know is that I'm part of a research center called the Wireless Institute at Notre Dame. And this is kind of an outgrowth of that original, combination of theory and practice. Now we have a fairly large team at Notre Dame. You wouldn't think of Notre Dame as a place that is a hotbed for wireless communications research, but in fact it is. The distinct way that we go about doing research is that we collaborate among the faculty, and we try to identify shared platforms that we can all contribute to and benefit from. And I'm going to highlight a few of those platforms here in the talk. But it's kind of a style of research that we've built there that's been a lot of fun. Okay, so software-defined radio platforms. As I said, we've done a lot of prototyping. We've been a little promiscuous with the tools that we've used over the years. We started, of course, as I said, with Edis and GNU Radio. For a while there, I drank some NI LabVIEW Kool-Aid and bought some very expensive gear to go after more standards-based prototyping. And then in recent years, we've actually been developing our own software-defined radio systems. And so I want to give you a little sense of those things as we kind of cruise through the talk here. So we'll start, there are basically 3 phases. We'll start with the EDIS and GNU Radio phase. When we got started early on, we wrote some tutorials. So we've always been trying to educate. And unfortunately, we never got those tutorials in a form that I was happy enough to make them broadly available or hand them over to the GNU Radio community. And unfortunately, with the GNU Radio evolving, those tutorials went out of date. But Dawei there made quite a name for himself along the way. We also got some nice funding from the National Institute of Justice to build some prototypes. And so this student, Brian here in particular, got pretty excited about building an integrated portable software-defined radio. The motivation was for a public safety communications gateway system. And he actually pursued a little startup company, won the McCloskey business plan competition at Notre Dame. We got some STTR funding from the Navy to continue working on that project. And so I guess what I want to plant here is that I can't do the kinds of research and teaching activities that I am most interested in doing, and I can't learn as much as I want to learn without great students like these. So as I started to develop this talk, I realized that I really want to emphasize the students and the great work that they've done along the way. We also started to promote using, instead of just building up laboratory capabilities, we started to do some work where the students actually prototype their research algorithms. So here's some examples of students whose theses were demonstrated on EDIS and USRPs in those days. I mean, we're in the 2008 to 2010 timeframe. We actually got a patent out of one of those lines of work involving spectrum sensing. And then we started to try to put the platform into the classroom. So this has been a 12-year saga of trying to integrate what we were doing in the labs, bring it into the classroom, sort of hands-on laboratory setting. And you see Glenn, one of the students there, teaching the students. And this has been a lot of fun. It's also really challenging because the electrical engineering students might understand signals and systems, but they can't program. The computer engineering students can program like crazy, but they don't understand signals and systems. So trying to teach across those two has been a really interesting and fascinating challenge over the years. The one thing I will say is that by the time we went through 3 versions of this, this particular run of developing a lab course. And by the 3rd rendition, we got a good textbook, which I'll come back to. And the labs got dialed in. There was a really positive feedback from the students. They really liked the hands-on approach. The combination of theory, and not just the vegetables of the theory, but also trying to build an over-the-air system that works. And so this is something we've remained committed to. The intent being, of course, not only to expose them to lots of interesting technology and prepare them for their careers, but in particular to accelerate their ability to do research using these platforms. This was also kind of a special moment. We participated in the original DARPA Spectrum Challenge. And so we had quite a lot of fun with this. Some new students came in. In this instance, we actually started to implement some of our own blocks at a very low level in the GNU Radio stack. So we had a pretty adaptive OFDM physical layer that these 2 grad students implemented. And we had the fortune of hanging out with Matt over a beer after the challenge was done. So that was a fun exercise. Then something completely different. Michael Dickens is probably in here somewhere. You here, Michael? Oh, he's out at the registration desk. I thought he would be here. So Michael came along. He had been working in industry, and he was quite a software developer. And we identified a direction for him to pursue as a PhD thesis. And at the time, the idea, there was early stages. We had some funding from NSF, and NVIDIA was interested in providing support to universities to use their GPUs. And so Michael was excited about the idea of heterogeneous processing, being able to develop a signal flow graph and schedule or reallocate the resources of the processing across that flow graph in a dynamic fashion. We tried to do that with GNU Radio at the time, and his conclusion was that we couldn't do it with GNU Radio. So he ended up writing his own software-defined radio framework to enable that and prototype it. It was called Surfer. And unfortunately, like many things that we've developed in our labs over the years, we never released the code. We never commercialized the code, and we never released the code. So one of the things we want to do here in re-engaging today is maybe exploring whether or not it makes sense to try to contribute this to the community. Because with AI and the growth of GPUs, there might be some interesting technology that he developed there. Okay, so again, we got another set of directions here. We pursued some more standards-based prototyping. So 2 of my PhD students got involved and started using NI hardware. They're still USRPs, of course, but they're plugged into the PXI chassis. We also started using the LabVIEW communication suite. This was driven largely by the fact that InterDigital was interested in evaluating the NI platform and the application frameworks for their Wi-Fi standardization efforts, and they came to us and asked us if we would consider doing some work on 802.11ax. And so, like many things, I thought, hey, there's lots of great things to learn here. Let's dive in. And I had some NSF funding at the time to get this hardware. So between Notre Dame and InterDigital and NI, we had this triangle of collaboration trying to prototype 802.11ax in our lab. We also did some work. This was specifically uplink multi-user MIMO. So these 2 grad students, Hamed and Mingming, did a lot of work to prototype and make changes and get involved at the FPGA level over the years. And so we've had some exposure to that as well. All of that work was really hard for the individual students to pursue, and as you probably know, the model at NI changed, and so the amount of support that we received at the time has kind of evaporated, and so we've moved away from the platform and its level of complexity. In recent years, we've been developing some of our own hardware, smaller, cheaper, lower complexity, but as a team, and I wanted to give you a quick sense of those 2 projects here today. So one project is called RadioHound, and the vision here is to create a really low-cost, receive-only RF sensor to try to monitor what's going on in the radio spectrum. And so just to give you a quick status, we've been developing this for about 6 years now. That we made a major pivot, largely inspired by my colleague Bert Hockwald, who's leading this effort. Made a major pivot to develop our own hardware. And so what you see here is the version 3 sensor. It's built upon the BeagleBone Black host computing platform. And then we have an RF card that plugs in. It also has GPS to be able to timestamp and location stamp the data that we receive. The vision here is to create something like Google Maps for the radio spectrum so that we have a ground truth as to what's going on. We've been developing this sensor in our labs now, and we've gone through 3 versions. Most of this work has been driven by our graduate students. So of course, advised by the faculty, supported by a growing set of technical staff. But the version on the far right, that entire development was led by one of our graduate students. He finished up his PhD, went to Qualcomm, and his reaction was that he felt like he was 2 years ahead of his peers because of this hands-on work that he did in our labs. So we're pretty excited about that. The signal processing that's on the nodes is relatively simple. It's Python and NumPy based. Try to really reduce the amount of dependencies because it's a small embedded computing platform. But the software stack for managing a large, the vision here is that we're going to manage a large network of these sensors. And this kind of concept of spectrum inventories and spectrum surveys has been explored in various ways, but we're really thinking about large scale, wide area deployments of these sensors. And so we've been developing a software stack using as many open source tools as we can, MQTT in particular as the messaging protocol, but we have an ability to control the sensors, send them jobs, and then start to visualize the results. We've actually taken this stuff out of the lab in a few occasions. So originally this was being co-developed with the Army Research Lab for electronic warfare type applications, electronic support in particular. So we've taken that out to a field test in the desert. Most recently, we've took it on the road with the FCC and the Postal Service as a pilot project to explore whether or not we could use this for the broadband mapping initiative that the US is pursuing. So that was done. This is actually that figure there shows the box that was mounted in the post office trucks. So that inside that box is a small RadioHound sensor, 3 mobile phones, 1 for each major carrier, and then a hotspot to convey the data back. So as it turns out, many of the logistical problems were associated with powering those smartphones and keeping those smartphones cool. The logistical problems were not with the RadioHound sensor for the most part. So we built up a fairly large team. One of the lessons learned here is that it takes a team, and so it can't be just one student to help us continue such a project and evolve such a project. So we've matured our center's operations by ensuring that multiple faculty see value in the project, and we've actually hired technical staff to provide some continuity as students come and go. But each and every student comes through and makes a major contribution, either as part of their thesis or just as a side project. So that's the RF sensing side of the equation. I want to come back to the courseware side of the equation. So in the last 4 years, I should say, we've had some funding from the ONR STEM program to come back to that undergraduate lab course and to integrate more concepts from interference, limited communications, and even electronic warfare, although we don't come in too heavy with the electronic warfare side of things. And so this is a project that I've been leading, and we've had a lot of fun with this. What we've done is use the same analog devices chips that we use for the RadioHound platform. There's corresponding transmit chips, and the ADALM 2000. So we've really tried to lower the cost and complexity of the lab kit that we're using. We also are committed to having the students build up the radio step by step. So they start at baseband, and then they add an up converter and a PLL, they add filtering, they add amplification, and that gives us an opportunity, even the antennas. They trim the antennas themselves to get the resonance at the target frequency. That gives us the opportunity for them to get exposure to all aspects of the radio, not just the software side. And I've actually enjoyed this a lot because I've been learning a lot about the hardware side myself. I started as primarily an algorithms and theory guy, and I didn't realize how much I didn't know about radio hardware. So there's a sequence of labs that we've developed. We're using primarily, again, Python, NumPy. The stack is relatively simple, although we do have a flow graph that's sort of like a very light version of what GNU Radio tries to do, or does. And the sequence is to build things up. We start at baseband, we start with wireline, then we add a transmit side, the receive side, then we start to clean things up. And ultimately we end with the ability to transmit over the air, real time, QPSK with coherent demodulation. We estimate the carrier offsets and timing offsets. What we found in this process is that most classes don't do a good job teaching synchronization, which is half or more of your radio. And so most textbooks don't do a great job with covering that subject, which is really, really frustrating. So we've had a lot of success here. The labs are generally very highly regarded by the students. In one offering, we had COVID hit us in the middle of the semester, so we had to go entirely remote. So we used TeamViewer, and we allowed students to access the hardware from remote, and that worked out pretty well. We're in the process of collaborating with the NTIA Institute for Telecom Sciences as part of a broader education and workforce development effort to continue to mature this courseware. And I want to acknowledge again, it's a team effort, a variety of students, and again, Bert Hockwald and John Chisholm, who really helped me understand the hardware side. So I just wanted to blast through that set of projects to give you my, kind of help you understand where I'm coming from as I come back to the GNU Radio community, because I've been away for a while. And what I thought I would do is try to offer some suggestions to this community here today, and I'll be around and I'd be happy to talk through some of these things and explore opportunities to collaborate on them as we go forward. So I have 5 suggestions for this community for your consideration. And this is all based on that backdrop, right? So the first one is, I think we need to kill the term software-defined radio. I hate to say that, but I think we do. I haven't seen a software-defined antenna. I haven't seen a software-defined low-noise amplifier. So what I have seen, by contrast, is a growing amount of configurability or software control of the radio front ends, and also the data acquisition systems. Okay, plenty of software-defined baseband or even IF. But when we think about a radio, we have to think about all these parts. And I think if we do so, if we make this shift of perspective, one, it will be more honest to the students. I found that students, they pick up the software-defined radio, they get to a certain point, and it's very hard for them to debug. They try to accomplish something with GNU Radio and an EDIS USRP. As awesome as they are, they hit a point where it's very hard for them to debug that system, primarily because they don't realize just how much hardware and just how much physics and just how much quantum noise effects are involved in building a radio. And so my suggestion is something like software-heavy radio or software-based radio. The other thing I think is interesting here, and we're starting to see this a little bit, say, in the 3GPP standardization efforts, is the notion of abstracting the details in the APIs between these different parts of the system. So for example, in 3GPP 5G cellular, they are talking about antenna ports. So they have an abstraction layer between the baseband and the actual antenna hardware. It's pretty interesting. We could probably pursue similar kinds of abstractions here. So that's one suggestion. The second suggestion is to really put more emphasis on courseware. This is hard. This is really hard to do, to present courseware to students that empowers them and encourages them rather than discourages them, with all the challenges of building these radios and getting them to work. There are some great textbooks that are out there. I'm going to go ahead and stay committed to the textbook by Mike Rice from BYU. This is the textbook that I use that's the closest to the sort of perspective that I use in my class. Mike developed this, and it was published under Prentice Hall, and it went out of print for a while. And then he thankfully got the rights back, and so now he's self-publishing this book. So the book on the left is great because it takes a discrete time approach. So it's one significant step in taking all the theory of communication systems, but getting it closer to modern radio hardware by taking the discrete time approach. He does a lot with synchronization, but primarily feedback-based synchronization, PLLs. He doesn't do as much feed-forward synchronization, which is what we see, kind of prevalent in Wi-Fi and cellular standards today. The reality is that there's a combination of the two, and it's often a very sophisticated combination. But being able to teach that to students and having a textbook is really important to students in the classroom. There are some other great texts here, right? These other texts, particularly Robert Heath's, is tied to Robert Heath's is tied to NI hardware as a platform, and Alex Wiglinski and company did a textbook, which is actually free. You can go download it from the Analog website, which is pretty impressive. It's tied to the Pluto hardware. So as I look at this and I kind of thinking about repartitioning things, what I'd like to suggest is maybe consider a series, a very, very tightly edited series of books, one which teaches the concepts in kind of a platform agnostic way, and then potentially lab manuals that go into details on a specific platform and go through lab exercises for that platform. We're more or less trying to structure the RadioWare pursuit that way, but we'd be, one group at one university can't solve this problem. So we're happy to try to work on collaborations toward this direction. So that's the second direction. Third direction is, in the interest of getting more people involved in this community, I think we should continue to add capabilities and lower costs. And so two examples in my experience that I think are doing great jobs with this are the Analog Devices Pluto platform. And also I've received a lot of feedback that Anaconda or Miniconda, whatever you want to call it, is really making it easy for folks to get involved and start to apply these tools. So I would encourage more of that. At the other extreme, I think this community can make more use of these really advanced wireless test beds that we've been building here in the US. So just so I know, how many of you are aware of the platforms for advanced wireless research? All right, this is $100 million of investment sponsored by the NSF and a number of industry players to build large-scale test beds at select locations throughout the US. There's one in Salt Lake City, there's one in New York City, there's one in Ames, Iowa, and there's one in Raleigh, North Carolina. There's also a very sophisticated, large-scale wireless channel emulator that started at Johns Hopkins as for the DARPA Spectrum Collaboration Challenge, but then migrated to Northeastern University. That's called Coliseum. There's something like 256 USRPs at your disposal to program and then have a massive network channel emulator to take the types of prototyping that we want to do in our labs, take them up to a much larger scale. So I would encourage this community to make use of these platforms. The folks that are working hard to build these platforms and making them accessible are more than happy to have you use them and help you use them. And they want to capitalize on this significant investment that's been made. Okay, the last suggestion that I wanted to plant is that it's great if we can encourage more folks to pursue advanced degrees. Okay, there's so much to learn, and you get paid to do it. There's plenty of funding. Chances are, if you're working somewhere, chances are your company would be absolutely ecstatic for you to advance in your career, deepen your knowledge, and make these kinds of contributions. as a nation, we need to see more of this, right? Across the board. So I just wanted to plant that suggestion as well. Okay, so those are the main things I wanted to do in terms of reflecting and offering those suggestions. There is one more thing I wanted to summarize here today, and that is a new national center called SpectrumX. How many of you have heard of SpectrumX? Awesome. Now at the end of today, all of you will have heard about SpectrumX. There's a lot of funding going into wireless in the US, across the board. This is another initiative from NSF. It's called the Spectrum Innovation Initiative. So NSF has a group inside, across multiple directorates in NSF that are concerned about spectrum, radio spectrum use, for science, for telecommunications research, and so on, for workforce development. So they have a coordination group that put together this Spectrum Innovation Initiative. One program in that initiative is called the SII Center program. And this is a 5-year, $25 million center. There were 14 teams that, as I understand it, 14 teams that submitted to this, solicitation to try to win. And we're really fortunate that we're leading the winning team, which is called SpectrumX from the University of Notre Dame. We put together we merged planning grant teams led by Notre Dame, University of Colorado Boulder, University of Virginia, and Olin College in Massachusetts. So this is a really exciting initiative. It's not your traditional NSF grant. It's a large-scale center. Of course, we're going to be doing research, but there's a significant emphasis on education and workforce development. There's a significant emphasis on collaboration, policy outreach, and so we're doing a lot to interface and interact across the spectrum ecosystem, as I like to call it. So there's a lot of interesting activities going on in the radio spectrum, of course. You know, you've probably heard of the National Spectrum Consortium, which is driven out of DoD. This is something akin to that, funded by NSF, smaller scale, unfortunately, but there's a number of other hubs in the ecosystem that are pushing really hard and doing some great things. There's really not an academic hub in the spectrum ecosystem. And so SpectrumX is meant to be that academic hub that interfaces with all of these other activities. We have standing working groups that are trying to pursue strategic research, education, and collaboration opportunities. And so I just wanted to highlight a couple of things about our program. So first of all, research. We're really focused on interdisciplinary research, from the antennas to the algorithms, to the applications, to the economics of radio spectrum. And the main thing I want to convey to this community is we currently have 6 project teams that we've prioritized research under SpectrumX. These things will evolve over time. That's part of the strategic planning process. We're starting year 2, but there's a lot of room for software-defined radio experts to contribute to this enterprise. Probably not surprisingly, given the emphasis on spectrum sensing that I mentioned earlier and the work that we're doing at Notre Dame, we have a big push on spectrum sensing, wide-scale deployments, low-cost deployments. And then we correspondingly need to think about the cloud counterpart to that that's going to absorb all of that data and allow us to manipulate it and apply machine learning and AI techniques to it. But also in terms of coexistence with scientific receivers, with active transmitters and DoD transmitters, there's a lot of opportunity for prototyping and demonstrating these kinds of concepts using software-defined radio. So we would encourage you to explore these opportunities and get involved. On the education side, we're developing curricula. Again, it's cross-cutting, interdisciplinary, so that people have an awareness not just of the hardware and software of radios, but more broadly the context, the economic, the regulatory, the policy context of those technologies. So we're developing courseware starting at middle school. We want to make spectrum cool again and get kids excited about radio spectrum and radio technologies. We're going to have courseware at the undergraduate level and the graduate level that's going to be widely available. So many universities will be able to pick it up and use it for credit. And then we're going to be having a number of summer schools and summer research opportunities for students, and we'd be happy to have companies and other organizations sponsor those students along the way. We're starting to mature our notion of collaboration with industry and government agencies, so we're going to have a relatively low-cost membership fee to get involved and participate in our center and help us steer how we allocate our funding. And so we would encourage, again, companies and agencies to get involved there to help influence, to engage and participate in our meetings, and then to have access to everything that we do. So that's my flyby of SpectrumX, okay? The overarching message I want to say is that basically because of Matt Edis, I got into software radio, and he helped me along the way, so thank you, sir. Because of Michael Dickens, we matured that, so thank you, Michael. And because of Bert Hockwald and my other colleagues at Notre Dame, we really developed this collaborative model in the Wireless Institute that we've now scaled up to a national center. And we have 27 universities, a number of industry and government agency collaborators. And my takeaway message for you all today is, we want to invite you to get more involved. And so here's how you can do that. Thank you very much. Happy to take any questions if you have them. Comments or feedback are welcome too.
So thank you, Dr. Laneman. You mentioned early in the talk that you had moved away from GNU Radio as a tool. Can you elaborate on some of the reasons why GNU Radio might not have been the right tool for your particular audience?
Yeah, and in fact, Michael can probably help with this question as well. When we started to build this Radio Hound sensor, the initial attempt was to use GNU Radio to control its tuning. So more or less what it's doing is it's doing a sweep across the spectrum. My recollection is that it was really hard. We would have to tear down the flow graph and reestablish the flow graph to change the frequency at that time. And so Michael did a lot of hard work to try to break that and make it work better. And ultimately, as a team, we just decided it was too complicated, and we basically went to creating something like UHD for our hardware and much more direct access to the hardware. I did have a student, it was an undergraduate student, and we had a small STTR contract to build a little OFDM transmitter. And so as an experiment, this was probably in, I didn't highlight it here, 2014 timeframe. I just handed him a couple of NSB210s, and I said, go learn GNU Radio, use the existing OFDM blocks, and try to close a link. And because we were assessing whether or not in this newest version of the course to use GNU Radio and the B210s as our platform, it was just extraordinarily difficult for him to debug. Simply put, it was just too hard to debug. And if I were to oversimplify things, I think there's this challenge because if you pick up a textbook and you try to understand signal processing, somehow that looks very different than the way that GNU Radio presents these blocks, and there's too big a gap. So the way I was describing it to Derek when we were chatting is that it'd be great to try to close that gap so that the abstractions and the nomenclature are closer together, so it's easier to get the conceptual understanding to correspond to what you see in the software. Right, at that time in 2014, it was just too wide a gap for him to be able to make sense of it. So we ended up basically building, again, doing a simpler version. It's not as general, it's not as high performance, but it's easier for us to debug and maintain.
No, thank you for that explanation. Makes a lot of sense.
Actually, I have a quick question. The course material you referred to, is that publicly available by any chance?
I would say that's one of my greatest failings, is that we have not released the stuff that we should be releasing. If we don't, at a certain point, if we're not going to do more with it, we should release it. But I'm always hesitant to release it if I'm not happy with it. So there's a tension there. So we do want to, we're using GitHub. All I have to do is flip a bit and it becomes a public repository. But we're in the process right now of having it vetted with the Institute of Telecom Sciences. We're probably going to add some more content, and my hope is within a year or so it becomes more open.
Okay.
But certainly on a sort of, what do you say? Sort of a partner release, we'd be happy to talk about those kinds of interactions, which is what we're doing with ITS.
Okay, yeah.
Hi, first, thank you. As part of the sort of GNU Radio leadership, I just want to thank you again for this keynote, because I feel like we asked you for a keynote, but we got much more than that. We have like some tangible suggestions, and I think going forward, anytime anyone's going to ask me about setting up sort of wireless teaching, I'm just going to point them to this YouTube video. I'm just going to say, watch that, and then come back, and then we'll have a conversation. I think you set an amazing groundwork there. I do have a question though. Do you find that that things being open source is actively helpful in education, or do you think it doesn't really make a big difference to the students?
Well, like many things, so just make sure I understand the question. Do I like the open source model for education or not? Is
Well,
that the question?
do you think it makes a change in quality when the tools and utilities that students have access to are actually open source, and you know they can look into all pieces of the stack, etc.? Or do you think it in the broader scheme that's not a major, I don't know, factor?
It's a double-edged sword, and I think it's about managing expectations. So, you know, I'll use an analogy of Microsoft Word and LaTeX, right? A student can, or even Google Docs. My 12-year-old can create a nice presentation in Google Docs today, but he can't write math in that presentation very effectively. He would have to learn LaTeX. So if I gave him LaTeX, he would get turned off. He would get overwhelmed and turned off by it, right? So there's a delicate balance, and I don't know how to solve that yet. What has been developed in the GNU radio community is absolutely amazing, but it's overwhelming to the uninitiated. And so figuring out how to, you know, one question I have in my mind is this: how do you think about developing someone from an apprentice to a journeyman to a master, right? I think you have to be a journeyman or a master to really do a lot of work in the GNU radio community. At least the last time I did a deep sample, it was really hard for literally one of the brightest undergraduate students I've ever had. He got accepted at MIT to pursue graduate studies. He really struggled to use the built-in OFDM blocks to close a link. And if we can lower that barrier for students like that, it's a win. So it's great to have all the resources and the community involvement, but I think getting it distilled down in a way that students get encouraged rather than discouraged would be wise.
Thank you. This is really good on-point feedback. Do we have any other questions while I'm holding the mic? There we go.
So with the level of difficulty of undertaking, like looking at spectrum and doing radio work, especially for the with providing stuff for middle school students, as you mentioned, what sorts of activities and whatnot do you anticipate being applicable for that grade level?
So the beautiful thing is I'm not the expert on that audience, and I would never be so bold as to try to pontificate on that. But through Spectrum X, we've been able to recruit a number of middle school and high school teachers. Okay. They had a workshop over the summer, so we presented a lot of this material to them, various aspects of radio technology, the radio spectrum, and so they're developing courseware to figure out how to bring it into their classrooms.
Okay, okay, awesome, thanks.
So stay tuned on that. We're looking forward to see what they produce.
Any other questions? Oh, there we are.
Having been out of school for a couple of years, when we were doing this in MATLAB and Simulink, and I feel like GNU Radio is very similar to Simulink, where we have lots of blocks. You're building this signal processing in each one of the blocks. I guess the question is, what is the disconnect you feel at the student level that would help GNU Radio bridge that gap that breaks it from the textbook, where they're learning those algorithms and being able to put together blocks in a processing block? What is that gap you're seeing there? I hear there is a gap, but I'm just trying to think, what is the piece that gets them through that gap from seeing that there's a block you've got to put processing in, you've got the data flowing through, understanding that digital signal processing as it flows through?
So I don't have it entirely figured out yet. It's a work in progress. Given my background, I think the challenge is that at a certain point, you know, taking that flow graph and mapping it to computational hardware and scheduling, it becomes a computing problem that many engineering students, electrical engineering students who are pursuing communications, they've never thought about that. So fortunately or unfortunately, right, software-based radio has a lot of ingredients, and instead of just focusing on, say, the signal processing or just focusing on the hardware, I think we need to take a fresh look about this modern view of what is a radio and give a little taste of each so that they have a sense of the landscape, and then create the opportunity to go deeper. in those various aspects. Like I want to now I have my flow graph, it works at a certain level of performance. How do I go and optimize its execution on this kind of computing platform? That's an entire field of study in itself, right? And I think if I were to oversimplify, if I just slap something together in Simulink or in GNU Radio, in GRC, I don't have that context of, oh, this has to map to the computer. Is it going to fit? Is it going to work? I think that taking a step back and giving the full view of the system, and that's why I think if I oversimplify it, the phrase software-defined radio is misleading. It promises to a student more than it can deliver, right? And that actually leads to the discouragement. They try to build something and it doesn't work and they don't know how to debug it. But if we take a step back and we say, look, this is a big complicated system, we're going to go through the entire process with the simplest possible waveform first. But then you see every part of the process, including taking a measurement in the lab and verifying that what you're seeing in the measurement is consistent with what you would expect from a theoretical point of view. Closing that loop, building that confidence on the simplest possible story, waveform, and then start to add the complexity. That's my gut instinct and my kind of the direction we've gone with this latest version of our course. So we do on-off keying and rectangular pulse shaping, literally the simplest waveform you can do, but we do all the synchronization, all the measurements along the way to build that confidence so that when you start to see more complicated aspects, and like one student, for example, smartest kid in the class, tried to implement OFDM on top of our baseline structure, hit a brick wall computationally. But he had a really solid foundation by that point. He didn't start off trying to do OFDM. So again, it's a work in progress, but I think it's an important set of issues to figure out. Did I get you? All right.
All right. We're out of time for questions. Will you be around for another few more minutes? There's a couple of gentlemen here already.
Yeah, I'm going to hang out for the day.
Excellent.
So, I would love to chat and kind of re-engage with the community and see if we can do some cool stuff together. Thanks.
Okay. Well then, a big round of applause for our keynote speaker.